Welcome back to our session. We're still discussing the redox reactions. So we are essentially saying that, there are many different ways at which we may look at the same reaction. You can think of an oxidation half reaction in terms of loss of electrons or multiple electrons, or actually, a substance actually donating electrons. So both perspectives are actually correct, but then the language again plays a very, very critical role in terms of understanding exactly what happens at a particular level in as far as the electron transfer occurring between a reducing agent and an oxidizing agent. Now let's look at more of these tangible examples, right? Okay, so consider the following reaction between a metal and acid. By now, you should be able to remember that when any metal, a metal reacts with an acid, we get salt and water. That's the general reaction between an acid and a metal. Now, if for practical example, we can take zinc as a metal, this is a balanced equation between the reaction between zinc and hydrochloric acid. It gives us our salt, zinc chloride, and hydrogen. So the reaction has already been balanced for us. Now the question that we can put across at this point in time is, what type of a reaction is this? Is it an acid-base or a redox reaction? Now remember the 6 and 9 analogy. Can we think of this as an acid-base reaction, or we can think of it as a redox reaction? Now, one may, depending on how you look at it, both options, possibilities are actually correct. But now, let's look at exactly what happens in terms of the redox reaction, right? But also, one can think of this as a gas-forming reaction, okay? That's another possibility beyond just acid-base or redox, right? Okay, now, if we react zinc and hydrochloric acid, is this an acid-base reaction or a redox reaction? That's what we want to understand. But also, beyond that, we are saying that if you remember the theories of, in terms of acids and bases, we know that an acid, is a proton donor, a base is a proton acceptor. All these ideas come to mind. So depending on your perspective, you can think of this as an acid base, but how exactly is this a redox reaction? We've also mentioned that this could be thought of in terms of a gas-forming reaction because hydrogen gas is actually released, right? But we know this is an acid, okay, because it contains the hydrogen atoms, right? Okay. Right now, if we want to write down the oxidation reduction half reactions, let's keep track of what happened to zinc. Now, if you look at zinc, the oxidation number of zinc on the left-hand side is 0, okay? And of the same substance on the right-hand side is actually 2+, okay? Now, the oxidation number of zinc has actually increased. And what is it that we know by now is that if a substance, if its oxidation number increases, that substance has actually undergone loss of electron. So we can think of this equation in terms of zinc, undergoing oxidation to give us zinc 2 plus 2 electrons. So that's our oxidation half reaction, right? So that's our oxidation half reaction. What about the reduction half reaction? Now, if you look at hydrogen, for argument's sake, in this case, the oxidation number for hydrogen is +1, okay? It's actually +1, okay? And then on the right-hand side, according to the rules of assigning oxidation number, this is equals to 0, all right? So we can also immediately say, okay, hydrogen actually undergoes reduction. And how does that happen? We can simply say that 2 of these hydrogen, okay, plus 2 electrons, which were lost by zinc, it can give us H2. So this is our reduction half reaction, if you can think of it that way. So indeed, one can then safely say that this is a reduction half reaction. And also, you'd realize that for chlorine, it's -1 this side and -1 that side. So chlorine is actually not involved in the electron transfer. So these are the oxidation and reduction half reactions in as far as this reaction between a metal and an acid. All right, so we are happy with that. So if zinc undergoes oxidation from oxidation number 0 to 2+, we are saying zinc is actually the substance that undergoes oxidation, which is a reducing agent. Okay? Okay, but there's something very interesting about hydrogen. We said, in as far as hydrogen is concerned, the reduction of reaction is 2H plus 2 electrons, okay, to give us the hydrogen gas, okay, in that sense. So the substance that undergoes reduction is the hydrogen ion in the acid. So this is our oxidizing agent, okay? So the oxidizing agent here is not the acid, it's actually the hydrogen ion. So if we were to write the formula of the substance, it would be H+. So the H+ is actually the oxidizing agent. Very, very important. So these are substances that undergoes specific processes, right? Okay? So if you think of a metal that has been displaced by hydrogen from the acid, this is a gas-forming reaction, as we have said, okay? So if you go back to that equation, you see that the zinc has actually displaced the hydrogen, okay? If you want to think of it that way. So the acid becomes the salt according to that general reaction, right? Okay, and also you're saying that the metal is the reducing agent. Why? Because it undergoes oxidation. So the process undergone by this reducing agent is oxidation, while the hydrogen in the acid, very, very important, is the oxidizing agent, because the hydrogen is the one that underwent reduction, okay? Very, very important piece of information, okay? And then the question, do all metals react with acid to form hydrogen? That's the big thing. Now we want to look at these displacement reactions. For argument's sake, if we take magnesium and zinc, okay, magnesium does displace the zinc, all right? So this is a possibility. So yes, is this a redox reaction? Indeed, because magnesium from 0 to +2, magnesium underwent what you call oxidation, and then zinc from 0 to from +2 rather, okay, +2 to 0, it underwent reduction. Is this a redox reaction? Yes, it is. All right. Okay. Now, is this a redox reaction? We agree, because magnesium actually underwent oxidation to give us Mg2 plus 2 electrons. Okay. While zinc 2+ gained electrons to give us zinc metal. Okay. So yes, indeed, this is a redox reaction. So we can actually do that. These are the half reactions that we are talking about, okay? So which talk about the transfer, okay? And then, again, identify the oxidizing agent and the reducing agent. So this substance that undergoes oxidation is our reducing agent, okay? While this substance which undergoes reduction, so this is the zinc ion, all right? This is our oxidizing agent, the one that undergoes reduction, okay? Okay, so it's all about the terminology. So magnesium displaces zinc from the solution. Yes, according to that reaction, we've managed to arrive at that, okay? Now, predict what would happen. Is zinc going to displace magnesium? Definitely not. This reaction will not take place, because magnesium shows a greater willingness, to lose electrons than zinc, all right? And then zinc cannot displace magnesium from the solution. So what does that say? It says to us that magnesium is actually a stronger oxidizing agent than zinc, right? Okay. Now, if we talk about the strength of a substance, so if we have a magnesium chloride, so already here, magnesium is magnesium 2+, while zinc has an oxidation number of 0. So if we compare the relative strength, it says to us that this reaction will not take place. But why does this reaction not take place? Because if we compare what we call, the strength of a reducing agent, First of all, the big question that we need to ask ourselves is, what exactly is a reducing agent? It's a substance that shows, more readiness or willingness rather to donate electrons to another. So if you compare zinc and magnesium, we arrive at a point that no, actually magnesium is more willing to give to zinc than the other way around. So we are saying that magnesium is a stronger reducing agent compared to zinc. That's the main point. So which explains why this reaction does not take place. So as a result, we are saying that magnesium is indeed a stronger reducing agent than zinc by comparison. Okay, we'll take a short break for now, and then when we come back, we'll look at more examples in as far as redox reactions. Let's take a short breather for now.